All right, let's dive right in. Today, we're demystifying one of the most essential building blocks in all of electronics, the amplifier. This is going to be fun.
So think about it. At its heart, amplification is all about this one question. You know, when you crank up the volume on a great song, you're taking this tiny, little electrical signal and making it powerful enough to actually move speakers and create sound. But how do you do that without turning it into a garbled, distorted mess? Well, that's the real trick, isn't it?
You see, our goal is to build the perfect amplifier. But before we can do that, we kind of have to agree on what perfect even means in the world of electronics.
And perfect means this, a perfect replica. Look at that small waveform on the left. That's our input signal. The ideal amplifier takes that signal and spits out the one on the right, an exact but much bigger copy. The shape is totally identical, just scaled way up. This is what we call linear operation, and it's the absolute holy grail for high-fidelity audio.
But what happens when we don't set up our amplifier just right? Well, that's when a beautiful signal can get really, really ugly. And this is what ugly looks like. Yeah, instead of that perfect wave, we get this mangled, flattened-out disaster. This horrible distortion is called clipping, and it is the arch nemesis of any good amplifier. If you look at diagram B, the bottom of the wave is just chopped off. That's called cutoff. Then look over at C. The top is completely flattened. That's saturation. Either way, our signal is basically ruined.
So, how in the world do we avoid this mess? Well, the secret is finding the amplifier's sweet spot before we even send a signal through it. This whole setup process is called biasing, and at its heart is something we call the Q point.
So the quiescent point, or Q point for short, is basically the state of the amplifier when it's just sitting there, powered on but with absolutely no input signal. The best way to think about it is like a car's engine at idle. It's the baseline voltage and current we set up so that when the real signal finally shows up, the amplifier is perfectly poised and ready to go.
This graph here shows us exactly how to find that sweet spot. That diagonal line, that's the DC load line, and it represents every possible operating state for our transistor. The Q point, that little dot right there, is the specific spot on that line where we choose to set our amplifier's idle state. By putting it right smack in the middle, we give our signal the most possible room to swing up and down without getting distorted. And believe me, location is everything. If that Q point isn't centered, our signal just won't have enough headroom. It's kind of like trying to do jumping jacks in a room with a really low ceiling. Sooner or later, you're going to hit your head.
And this graph shows you exactly what happens when you hit your head. In the diagram on the left, the Q point is way too close to saturation, so when the signal swings up, bam, it hits the ceiling and gets clipped. On the right, it's too close to cutoff, so when the signal swings down, it smacks right into the floor. And just like that, we're right back to that awful distortion we were trying to avoid in the first place.
Okay, so we get it. We need to set the Q point perfectly. But how do we actually do that in a real circuit? And maybe more importantly, how do we make sure it stays put? Let's take a look at three common approaches. A tale of three circuits, if you will.
First up, our first contender is the simplest of them all, the base bias circuit.
I mean, it really doesn't get much more straightforward than this. You've got one power source, one resistor, that's RB, and that sets the base current, which in turn locks in our Q point. It's simple, it's clean, it's super easy to calculate. But there is a catch.
And oh boy, it's a big catch. Stability, or rather the lack of it. You see, the Q point here is massively dependent on a transistor property called beta. The problem is, beta can change wildly with temperature, or even just from one transistor to the next. So what happens? Our perfect little sweet spot starts drifting all over the place, making the whole circuit completely unreliable.
So the simple approach didn't work out. We need to get a little bit smarter. Attempt number 2 uses a really clever trick called negative feedback.
Now these circuits are a lot more clever. By either adding an extra resistor at the emitter or by feeding a bit of the output voltage back to the input, they create a self-regulating system. It's amazing, really. If the current tries to creep up because of heat, the feedback mechanism automatically pushes back, forcing it down. It's actively fighting to keep that Q point right where we want it.
So, what's the verdict? A huge improvement. These feedback circuits give us good stability, and they're way more reliable than that simple base bias method. But, you know what? We can still do better.
And that brings us to the undisputed champion of biasing circuits. This is the most widely used, most trusted method for getting a rock-solid Q point.
Ladies and gentlemen, the voltage divider bias circuit. Now, I know it looks a little more complex, but its design is absolutely ingenious. Why? Because it makes the Q point almost completely independent of those annoying transistor variations we were just talking about.
So, why is this the hands-down winner? It's all about those two resistors R1 and R2. Together, they form what's called a voltage divider that locks the base voltage to a specific, super predictable value. This means the circuit's idle state now depends on the stable values of the resistors, not the fickle, unreliable beta of the transistor. The result? Excellent, reliable, rock-solid stability.
So let's recap this whole showdown. Base bias, it was simple, sure, but its stability was so poor, it's basically a non-starter for serious work. Feedback bias? A good improvement, using that clever self-correcting mechanism. But voltage divider bias is our clear winner, with excellent stability because it essentially engineers the transistor's beta right out of the equation. It's brilliant.
So after all that, what is the one thing you really need to remember from all of this?
It all boils down to this. The secret to a clean, distortion-free amplifier isn't some magical, expensive component. It's the careful, deliberate engineering of a stable operating point. If you get the biasing right, you get the perfect signal. It's that simple.
You see, this stable amplifier is a fundamental building block. It's a reliable workhorse you'll find inside countless electronic systems, which really just leaves us with one final thought. Now that we know how to build this one little component perfectly, what incredible things can we build on top of it? Thanks for tuning in.